sorry for my conference again. So, okay, let's go back to my talk. And what I showed was the Lyman what I did was combining all available data in the literature. We really analyze the surface brightness profile and evaluate the size changes of Lyman halos as a function of redshift. And what we found was Lyman halo sizes Lyman halo sizes also decline toward higher redshift. And in previous studies, this Lyman halo size changes with redshift is expected to be described by the change of virial radius of host diagonal halos. So we also checked this scenario by assuming two models. So one is the dark halo mass of quasars host dark halo is constant over redshift. The other model is the dark halo mass is evolved. Evolved means we considered for example, dark halo quasars. For example, how can I say it? So quasars are redshift 5, for example. Also can be detected the quasars is in the same evolutionary track of halos, even at redshift 2. That is the other model that we mentioned, the evolved model. So first we see the constant model. So you can clearly confirm that the constant model is comparing to the constant model, our halos changes much steeper toward higher redshift. So the next we check the evolved model. Then we found a very good match. So this result probably indicates that the CCM traced by Lyman halo likely increase its size with cosmic time, keeping pace with the one of hosting dark halos. So it was just the final slide. So summarize. We investigated quasars Lyman halos wide redshift range and found these two kind of evolution of quasars Lyman halos. One is quasars Lyman halos with quasars H. The other one is quasars halos evolution with cosmic time. However, I have to say that our data, our results are obtained from very small sample size. So for example, redshift 6 results are obtained from only 4 quasars. So it means we cannot rule out the possibility that these results came from kind of coincidence of small sample size. So what we need is many samples, especially higher redshift, and also we need samples of quasars with both Lyman halo measurements and also infrared value. Because, for example, when we see this, this color indicates a redshift of quasars with Lyman halos. Then you can find, comparing to black hole mass sample, this plot, samples in this plot mean the samples with IR luminosity measurements are very small. So maybe in the future, Akari data, or if they are good quasar in the net, then I can increase this this plot. So thank you very much.
I think it's fair to give more extra time for questions. Okay, so please take that.
Could you go back to the early slide where you showed the surface brightness profile of the quasar halo compared to some other halos?
Ah, okay.
It's an early slide. Because one thing I don't quite understand about that is this halo is there. Yeah, okay, look at that. Well, all right. Okay, it doesn't have a comparison of everything, but okay, so there's the halo. It's goes down to about 10 to the minus, several 10 to the minus 18 at tens of kiloparsec. I recall on your other slide that the Lyman break galaxies have also halos that are maybe several times lower surface brightness, but they are nothing. I mean, in ionizing photons, this probably has hundreds of times more ionizing photons, and yet it doesn't seem to make that, you know, how could they have a Lyman alpha halo at all?
Do you mean why Lyman Blake galaxy have Lyman?
Right. I mean, is it the same process? It's the same thing, photoionization from this object?
Yeah. So actually, it's kind of quite good question because it's still puzzling. But especially maybe for that, this quote is much appropriate, I think.
Yeah, there. I mean, they're up at 10 to the minus 17 easily.
Yeah.
How can they do that? They have nothing compared to that quasar.
Yeah. So
pathetic.
yeah. So as I said in the introduction part, I didn't mention in detail, but in order to produce Lyman alpha halos, not only fluorescent, but also scattering of Lyman alpha photon produce Lyman alpha halo if neutral gas exists in the CZM.
Yep.
So maybe so this blue and green line indicate the Lyman alpha halo from Lyman alpha emitters and the Lyman break galaxy, and we expect, especially these two populations, so more like star-forming galaxies. Star-forming galaxies, Lyman alpha halos probably originate from the scatter light of Lyman alpha photons, because and even only the Lyman alpha photon, so scatter light, we still detect the Lyman alpha halo. Of course, the brightness is maybe 2 order of magnitude fainter than quasars, but still we can detect. And so it can be one possibility. But yeah, actually that's still puzzling.
Well, here's what we got. So we don't really know exactly what determines the surface brightness of this Lyman alpha emission. As you said, we need to know how many ionizing photons there are, we need to know how much scattering there is, we need to know how much CGM there is. It seems this could be a lot of different values for different objects.
Exactly.
So your idea to use, well, a sort of a standard size, to size of 10 to the minus 18, it seems that it would depend on many, many unknown individual parameters for each object that we look at.
Yeah, of course. So if we consider the more detailed origin or detailed physical mechanisms to create the Lyman alpha halos, we have to consider many parameters.
And we don't know the parameters.
Yeah, exactly. But but this study is more focused on to understand the average of the halo. So yeah.
I guess your main point is we need more objects.
Yeah, that is one.
And you have to spend like $20,000 to make another one of these filters.
And then maybe another important thing is we also need to investigate maybe a theory from the theoretical aspect. Yeah.
Would GTC have a tunable filter, right? So why don't you tune it and then take it one by one? Grand telescope canary.
I
At least you don't need to spend money. You just tune a filter and then bam. I think it's a good idea. You don't need hypersprang count.
Yeah, that's true. Yeah, I don't need a hypershifting cam. Yeah.
Other questions?
I'm not listening. So you find an interesting correlation between redshift and size and black hole mass and luminosity, right? Can we separate the effect of redshift and black hole mass and then maybe dark halo mass? Because these are also correlated, right? I think.
Yes. Yes.
So, for example, if we go higher redshift, I don't know, black hole mass is larger or smaller? I mean, actually, your black hole is smaller, right?
Your black hole mass estimate is just the square root of the luminosity. That's what it is. Anyway, so this object, of course, is less luminous than those others. So that's why we say it's a smaller black hole mass.
Well, yeah, so I wanted to ask a question if the redshift is more primary parameter or black hole mass. Can we separate these?
Not with 4 objects, I don't think.
Well, maybe not with 4, but the redshift 2, 3, 4, they are more, right?
Okay, so the lower redshift objects were also highly luminous.
Yeah.
Quasars.
I don't know how luminous they are, but recent news observation observed about 80 quasars halos. They, according to they're saying the survey is unbiased survey. Means they did not select their target from the luminosity of the quasar. So. But maybe still kind of luminous.
Yeah, I mean, somebody selected based on the luminosity.
So as we go higher redshift, the diameter of the halo is decreasing, right? But then the black hole mass is probably increasing here, right? Toward higher redshift. So.
Do you mean the mean?
Yeah, mean at redshift 2, 3. Generally speaking, because of the selection effect, high Z, or is that So then, if you naively scale black hole mass with diameter, then your decline might be even steeper if you just compare the same black hole mass.
Maybe, yeah. So do you mean this direction?
Yes.
Maybe.
But then what's really important is the halo mass, right? It's the halo mass, right? Dark halo mass. So I'm assuming black hole mass may be scaled with halo mass.
Yeah, but again, still our sample is very small, especially higher redshift. So.
But can we take the redshift 2, 3, 4, and then same mass range, smaller mass range, and then plot that.
Okay, I check it. Yeah.
Because if you increase a very small mass black hole, probably their halo size will be smaller, isn't it? So that effect might be in that plot.
Yeah. Okay, I check it.
Okay.
I have a question about the halo mass. So you showed the 2 different models. One is the constant halo, and the evolution. So I still just want to know what's the meaning of evolution. So what do you mean by evolution? Because so according to the hierarchical structure formation, then at the very high Z, so very massive dark matter halo is very rare. So in the low Z, so a lot of the massive dark matter. So this evolution is just due to this evolution of dark matter halo, or related to the some to host quasars.
So what we assume as evolved is quasars of each redshift on the same evolutional track of one halo. So it means, for example, the redshift 6, one halo is that halo who has mass of maybe 10 to 11, then it must be evolved 10 to 14 or 10 to 13 RSC2, right? And what we assumed was quasars are on the track of the one halos, such evolving like that. Yeah, yeah.
Okay, thank you.
Yeah, yeah.
Just that means this evolution following the evolution of the halo.
Yeah, exactly.